So there are 4 periodic table trends that you need to know for chemistry. And the 4 trends are electronegativity, atomic radius, ionization energy, and electron affinity. So for most trends, the value increases as you go to the right and as you increase. So in this general direction. The only trend where that's not true is for atomic radii, and we'll see why that is later. And something important to realize is that these noble gases do not follow these trends. So really we can just ignore the noble gases while we're referring to these trends. So in order to understand why we have all these periodic table trends, the only thing you need to understand is the Zeff nuclear charge. And if you understand the Zeff nuclear charge, you can understand why we have these particular periodic table trends. So let's analyze these particular elements. So let's draw these elements down here. So we know as we go to the right in the periodic table, we're getting more and more protons. For example, lithium has 3 protons, beryllium has 4 protons, boron has 5 protons, and etc. So we know as we go to the right in the periodic table, we get more of these positively charged protons. So therefore, it makes sense that these elements over here on the right are going to have a very positive Zeff nuclear charge. However, these elements over here are going to have a very weak positive Zeff nuclear charge. So it makes sense as we go to the right in the periodic table, these elements have a more positive Zeff nuclear charge. For example, comparing lithium to fluorine, we see that fluorine has a lot more of these positively charged protons. So it makes sense that fluorine is going to have a very positive Zeff nuclear charge. And this Zeff nuclear charge explains why we see all of these periodic table trends. So for example, electronegativity. We know electronegativity increases as we go in this particular direction. So therefore, electronegativity increases as we go to the right. Why is this true? Well, first we need to understand what is electronegativity. Electronegativity is an element's tendency to pull negatively charged electrons towards it. For example, let's say we have a carbon atom and a fluorine atom. We know electronegativity increases as we go in this particular direction. So therefore, as you go to the right, the electronegativity increases. So therefore, we can see fluorine is more electronegative than carbon. And we know the more electronegative an atom is, the stronger the tendency it has to pull negatively charged electrons towards it. So therefore, this fluorine is going to pull negatively charged electrons towards it. And this fluorine is going to hog all these negatively charged electrons. So as fluorine pulls negatively charged electrons towards it, it's going to gain a partial negative charge. Because again, it's hogging all these negatively charged electrons. And carbon's going to lose those negatively charged electrons, so it's going to get a partial positive charge. So whenever you have 2 elements bonded together, you compare their electronegativities. And the element that's more electronegative is going to have a partial negative charge because it's pulling the negatively charged electrons. So why is fluorine more electronegative than carbon? Well, again, we see as we go to the right in the periodic table, the elements get more and more positively charged protons. So therefore, it makes sense that fluorine has a lot of protons, so it's going to have a very positive Zeff nuclear charge. So because this fluorine has such a positive Zeff nuclear charge because of all these protons, it makes sense that it's going to attract these negatively charged electrons. So that explains why electronegativity increases as we go to the right. As we go to the right, we get more positively charged protons, so we have a more positive Zeff nuclear charge, so it's going to attract negatively charged electrons, and the element's going to become more electronegative. So what about the atomic radius? We see the atomic radius increases as we go in this particular direction. So why is this true? Well, to understand this, let's compare this lithium atom to a fluorine atom. Again, we know as we go to the right in the periodic table, we get more of these positively charged protons, so we have a more positive Zeff nuclear charge. So fluorine has a more positive Zeff nuclear charge compared to lithium. So it makes sense if we have these electrons orbiting around these atoms. Because fluorine has such a positive Zeff nuclear charge, it's going to strongly attract that negatively charged electron. So this negatively charged electron is going to be very close to this fluorine. However, because lithium has a very weak positive Zeff nuclear charge, it's going to very weakly attract this negatively charged electron. So this negatively charged electron is going to be rather far away. So this explains why fluorine has such a small atomic radius, while lithium has a large atomic radius. Because again, as we go to the right, we get a more positive Zeff nuclear charge. So fluorine has a very positive Zeff nuclear charge. It's going to bring that negatively charged electron very nearby because it's going to attract it. So we're going to have a very small atomic radius. So as we go to the left in the periodic table, the Zeff nuclear charge gets weaker, so it's going to attract negatively charged electrons more weakly. So these negatively charged electrons are going to be far away, so we're going to have a large atomic radius. So why does atomic radius increase as we go down? Well, as we go down, we see the element gets larger. It has more of these protons in the nucleus, so it's going to get larger. And just the way the negatively charged electrons fill up orbitals, they get further and further apart. So the atomic radius increases as you go down. So that explains why atomic radius increases in this particular direction. Also, something important to realize is let's focus on this carbon atom. So if you have a neutral carbon atom, it's going to have a certain radius. However, if you have the cation form of it, it's going to have a smaller ionic radius. However, if you have the anion form, it's going to have a larger ionic radius. And that's true for any element. When you have the cation form, it has a smaller radius. When you have the anion form, it has a larger radius. And this makes sense because if you have negatively charged, if you have the anion with the negative charge, you're going to have more of these negatively charged electrons. So it makes sense that the ionic radius will get larger. However, if you have a cation with a positive charge, it makes sense if you have more of a positive charge, it's going to attract those negatively charged electrons. So you're going to have a smaller radius. So atomic radius refers to a neutral atom's radius, while ionic radius refers to an ion's radius. And again, the rule of thumb is an anion is going to have a larger radius than a cation. So what about ionization energy? So we know ionization energy increases in this particular direction. So why is that true? Well, first we need to understand what is the ionization energy. The ionization energy is the energy required to rip off an electron from an atom. So why does the ionization energy increase as we go to the right in the periodic table? Well, let's compare lithium with fluorine. Again, we know as we go to the right in the periodic table, we have a more positive Zeff nuclear charge. So fluorine has a very positive Zeff nuclear charge, while lithium has a very weak positive Zeff nuclear charge. So because fluorine has such a positive Zeff nuclear charge, it makes sense that it's going to require a lot of energy to rip off this negatively charged electron. Because this negatively charged electron wants to be near this positive Zeff nuclear charge. So it's going to require a lot of energy to rip off this electron. However, because lithium has such a weak positive Zeff nuclear charge, it's going to be easy to remove this electron. So it's going to require very little energy to remove this electron. So now we can see why the ionization energy increases as we go to the right. As we go to the right, we get a more positive Zeff nuclear charge, so it's going to require more energy to rip off negatively charged electrons, because these negatively charged electrons like this positive Zeff nuclear charge. So for example, fluorine, if we want to rip off a negatively charged electron, maybe it will require 1600 kilojoules per mole. However, lithium, maybe it only requires 1000 kilojoules per mole. So therefore, we can see it requires more energy to rip off an electron from fluorine. So fluorine has a more positive ionization energy, a larger ionization energy. And again, it's because this fluorine has a positive Zeff nuclear charge that attracts these negatively charged electrons. So therefore, it makes sense that it's going to require a lot of energy. It's going to have high ionization energy to rip off those negatively charged electrons compared to lithium. But something important to realize is the more electrons you rip off, the more energy is required. For example, to rip off this first electron of fluorine requires 1600 kilojoules per mole. However, to rip off the second electron requires 3300 kilojoules per mole. And to rip off the third electron requires 6000 kilojoules per mole. So we see the more electrons we rip off, the more energy is required. And ripping off the first electron is referred to as the first ionization energy. To rip off the second electron is the second ionization energy. And to rip off the third electron is the third ionization energy. But we see as we rip off electrons, the more energy is required to rip off the subsequent electron. And that makes sense because once we rip off the first electron, now we have this positively charged fluorine with this positive charge. So therefore, it's going to require more energy to rip off a subsequent negatively charged electron. Because once we rip off that subsequent negatively charged electron, now we have a larger positive charge, which is going to attract those negatively charged electrons. So it's going to require even more energy to rip off the third electron. So as we rip off electrons, the fluorine gets more positively charged, so therefore it's going to require more energy to rip off subsequent electrons. And this is always true. The second ionization energy will always be higher than the first ionization energy, and the third ionization energy will always be higher than the second ionization energy. So let's try another example. Let's look at sodium. To rip off the first electron from sodium requires 500 kilojoules per mole, so that's the first ionization energy. However, to rip off the second electron requires 4,500 kilojoules per mole. So we see a huge jump from the first ionization energy to the second ionization energy. Why? Well, due to the location of sodium on the periodic table, we know once we rip off that first electron, now we have electrons resembling an octet. And we know octets are stable. So therefore, ripping off the first electron is pretty easy because once we rip off the first electron, now we resemble an octet. However, now if we want to rip off the second electron, we're destroying that octet. So that's why it requires so much energy to rip off the second electron. That's why we have such a high jump from the first ionization energy to second ionization energy. So whenever you're analyzing ionization energies, you should keep in mind octets. And we can see why ripping off the first electron is easy. It has a low ionization energy. However, to rip off the second electron requires a ton of energy because that's destroying the octet. And whenever you're destroying the octet, the ionization energy is going to be very high. So now let's talk about electron affinity. So electron affinity is the energy associated when an atom gains an electron. It's kind of like the reverse of the ionization energy. So let's compare the electron affinity of lithium compared to fluorine. Well, again, we know as we go to the right in the periodic table, the Zeff nuclear charge increases. So fluorine has a more positive Zeff nuclear charge relative to lithium. So because fluorine has such a positive Zeff nuclear charge, it makes sense that it's going to be very energetically favorable for fluorine to gain a negatively charged electron. So we can see why fluorine has a larger electron affinity compared to lithium, because fluorine has a more positive Zeff nuclear charge, so it's very energetically favorable for it to gain a negatively charged electron. So that's why electron affinity increases as we go to the right in the periodic table. So again, because fluorine has a more positive Zeff nuclear charge, it's very energetically favorable for it to gain this negatively charged electron because it's attracted to this positive Zeff nuclear charge. So when fluorine gains this negatively charged electron, it goes to a lower energy state by 330 kilojoules per mole. However, when lithium gains a negatively charged electron, it goes to a lower energy state by 60 kilojoules per mole. So we can see fluorine has a larger electron affinity compared to lithium. And again, that makes sense because fluorine has such a positive Zeff nuclear charge. When it gains a negatively charged electron, it's going to go to a much lower energetic state. Hence, fluorine has a larger electron affinity, and that's why electron affinity increases as you go to the right in the periodic table, because the Zeff nuclear charge increases, so it's more energetically favorable. But something important to realize is ionization energy and electron affinity are telling you the same thing. They're just looking at it from a different perspective. For example, the energy required to rip off a negatively charged electron from fluoride is 330 kilojoules per mole. However, the energy associated with fluorine gaining a negatively charged electron is 330 kilojoules per mole. So we can see the ionization energy and the electron affinity are telling you the same thing. They're the same magnitude, but opposite sign. And the point is, whenever you rip off a negatively charged electron from an atom, it requires energy. It requires energy to rip off this negatively charged electron. However, whenever an atom gains a negatively charged electron, it goes to a lower energy state. So again, these are telling you the same thing. The energy required to rip off this negatively charged electron from fluoride is 330 kilojoules per mole. That's how much energy is needed to rip off this electron. However, when this electron is added to this fluorine, when this fluorine gains this negatively charged electron, it goes to a lower energy state by 330 kilojoules per mole. So again, the point is ionization energy and electron affinity are telling you the same thing. And they're going to be the same value, but opposite sign because they're going in the opposite direction. But the point is we have these 4 periodic table trends. But the only thing you need to understand all these periodic table trends is the Zeff nuclear charge. As long as you understand the Zeff nuclear charge increases as you go to the right, and the nucleus gets more positively charged as you go to the right, as long as you understand the Zeff nuclear charge, you can understand these periodic